Right then, so we have the sheet titled At the Mercy of Newton. We have a pair of blocks, smooth blocks, resting on a smooth surface, and the lower block being acted upon by an external horizontal force, capital F. We want to find the acceleration of capital M. We want to be able to find acceleration of small m. Right? Now, would you want to believe that since capital M and small m are smooth, they will exert no tangential forces on each other? Friction would be zero, right? So if you think about it, the free body diagram of capital M is this, F like this. There is no force in the tangential direction because the surfaces are smooth. There is capital mg downwards, right? There is normal reaction R1 from the ground upwards, and small m will press on capital M with a normal reaction R2 downwards. Yes or no? Does it not summarize all forces on capital M? Right? So what would be the acceleration of capital M? Acceleration of capital M would be simply F by capital M. Yes or no? You got the same answer? Right. So acceleration of capital M would be F by capital M. Now look at small m. Free body diagram of small m. Small m. What are the forces acting on small m? Gravity downwards. Small m exerts on capital M R2 downwards. So capital M will exert on small m R2 upwards. Is this not the summary of all forces acting on small m? What's the acceleration of small m? Zero. See, there is no force in this direction on small m. So acceleration of small m will be zero. Realize that it is friction that would have driven small m to the right. Absence of friction means small m would be left behind. Small m would be left behind. There would be no acceleration of small m. Yes or no? It's about this pulley, fixed pulley, and a mass 2m resting on a horizontal ground, and there is an ant which is climbing up with an acceleration g by 2. An ant of mass small m climbing up this thread with an acceleration g by 2 as seen from the ground. I now want to be able to find the reaction of the ground on 2m. Reaction of the ground from 2m. Now, let me first look at the free body diagram of the ant alone. Let me look at the free body diagram of the ant alone. So ant, there is mg downwards, right? The string exerts a tension force T upwards on the ant, right? So there is tension force on the ant acting upwards. This is summary of all forces acting on the ant. What's the effect? G by 2. The ant has an acceleration g by 2 upwards, right? So this gives me like a T minus mg equal to mg by 2. T minus mg is mg by 2. T therefore is 3 mg by 2. Right? Now, let's look at the free body diagram of 2m. Let's look at the free body diagram of 2m. So what's the story of 2m? Story of 2m is 2mg downwards, 2mg downwards, normal reaction R upwards, and tension upwards, right? Tension upwards. And small m, 2m rests on the ground. That means net of all these forces must be 0. Net of all these forces must be 0. So I have like a R plus T taking care of 2mg, R plus T taking care of 2mg. So R therefore turns out to be 2mg minus T, where T we have computed as 3mg by 2. So that makes it mg by 2 is the normal reaction from the ground. Now, I want to compute the normal reaction without finding the tension. I now want to compute the normal reaction without finding the tension. I don't want to buy tension. Right? So what I do is, I restructure a solution. Did you understand all of this? This is fine, right? Now for the heck of it, I want to find a solution to the problem without taking recourse to finding tension in the string. Without taking recourse to finding tension in the string. That means somehow I would include the string as part of the system so that tension becomes an internal force and it would not have to be dealt with separately. What I do is I straighten the whole thing. This string, this is the position of the ant. This is the position of the ant A, and I straighten it up like I've done before. So if I straighten it up, this is where the ant is. If I straighten it up, then realize on straightening it up, this A will be like coming down. A is G by 2, which is coming down, right? There is mg still acting downwards, whether I straighten or I don't, on the ant, right? Yes or no? And the ant has an acceleration g by 2. As before, there is 2 mg downwards. 2 mg downwards here on this, and there is normal reaction r. So now, I'm not including tension. Why? Because tension is an internal force. I'm looking at a system comprising my small m, which is the ant, the 2m, and the string as one single system. Yes or no? This is the sum total of all forces. Why no tension here? Because the string has been included in my system. So tension becomes an internal force. When I drew the free body diagram of small m separately, or when I drew the free body diagram of 2m separately, then tension was an external force. But I'm looking at 2m, small m, and the string as one single unit. Right? So these are my external forces. I'll apply Newton's second law in the vertical direction. In the vertical direction, what are the sum total of forces acting on the system? mg, Mother Earth on small m. 2mg, Mother Earth on 2m. 2m minus r on the system, right? That must be mass of this into acceleration of this downwards, mass of this into acceleration of this downwards. Yes or no? What's the mass of this? Small m into what's the acceleration of this? G by 2 plus mass of this, which is 2m, into what's the acceleration of this? 0. 0. Yes or no? How about it? So realize that this becomes 0, r then becomes 3 mg minus mg by 2. Mg plus 2 mg. Oh, sorry, I'm so sorry. I'm so sorry. One mistake that I made here is when I straighten it up, I'm sorry, when I straighten it up, this mg would be upwards. See, when I see this is mg like this, when I straighten this, mg will be upwards. Yes or no? See, I'm straightening this. So this mg goes up. Yes or no? So that's a mistake that I made. Let's fix this. Let's fix this. I'm so sorry about this. So then, this is my new system with mg now like this. So what's the net downward force? The net downward force is 2 mg minus mg minus r equals mass of this into acceleration of this, m into g by 2 plus 2m into 0. Newton's second law applied on this. Net downward force is 2 mg minus r. Yes or no? Net downward force must be mass of this into downward acceleration of this plus mass of this into acceleration of this. Clear? So that gives me r equal to mg minus mg by 2. That makes it mg by 2. That makes it mg by 2. By looking at the equivalent system. Do you understand what we did by straightening up things? So the next problem is about a massless wedge moving to the right with an acceleration a somehow. We do not know. Something is causing it to have an acceleration a to the right. This is the mass small m. It's sliding down the plane, but is maintaining contact. Right? Now, do you realize that this is theta? If I look at the free body diagram of small m, what are the forces acting on small m? Tell me. Mg like this, right? Mg like this. Then there is normal reaction like this. This n makes an angle theta with the vertical, right? Yes or no? Right? Now, would you want to believe that if the plane has an acceleration a to the right, if the plane has an acceleration a to the right, look at their common normal direction. This is their common normal direction. For small m to maintain contact with the plane, right? Would you not want to believe, see, this angle is theta, this is also theta, right? Along the common normal, they must have the same acceleration, right? This is the common normal. What's the acceleration of the plane in this direction? Do you realize this angle is theta, so acceleration of the plane in this direction is a sine theta. Yes or no? Right? So in this direction, the acceleration of small m must also be a sine theta. That's a wedge constraint, right? That means the acceleration of the mass m in this direction must be a sine theta, so that contact could be preserved, right? So I can apply Newton's second law in this direction. So n minus mg cos theta must be mass into acceleration in this direction, m into a sine theta. So what's the force acting on this? Normal reaction is m into g cos theta plus a sine theta. You got the same answer, right? So you know, there is a block of mass capital M and resting on a smooth horizontal surface. There is small m on the vertical edge of capital M. This surface is also smooth, all right? Now, what all is going to happen? One thing, do you realize that I will assume that capital M and small m maintain contact. For them to maintain contact, in the common normal direction, should they have the same acceleration? Yes, in the common normal direction, they should have the same acceleration, right? So if I look at capital M plus small m together, capital M plus small m together, then the only horizontal force external acting on the system is capital F. Why? Because the normal force between small m and capital M is now internal. It will not be represented when I look at capital M plus small m together, right now? So can I say capital F is capital M plus small m into A? So the acceleration in the horizontal direction is going to be capital F by capital M plus small m. So if you look at capital M alone, then capital M has no vertical acceleration because there is normal reaction which accounts for any vertical displacements, right? So this acceleration remains A of capital M. So capital M has a rightward acceleration, but small m has two kinds of acceleration. One, along the common normal, it shares a common acceleration with capital M, but realize that there is a downward force acting on small m. On small m, what is the free body diagram of small m? There is mg like this, right? And capital M exerts on small m a normal reaction n like this. Capital M will exert on small m a normal reaction n like this, which provides small m an acceleration a to the right. A we have computed. So can I compute n? What is n? Must be m into A. The normal reaction between capital M and small m would be m into A, which is m into capital F by capital M plus small m, right? Now, so that's the horizontal acceleration of small m. But in the vertical direction, does it have an acceleration? How much is it? G, right? G, huh? Right? Because there is no friction. Friction would have prevailed in this direction. So the only vertical force acting on it is mg. So it has a downward acceleration Ay equal to g. Yes or no? Yes or no? That means small m, if you are a ground observer, what would you see on small m? An acceleration ax, which is the same as a that we have computed, and an acceleration ay, which is g. For a ground observer then, what would be the net acceleration from a ground perspective? This would be the net acceleration from the ground perspective. of small m, right? So from a ground perspective, the acceleration of small m was going to be root ax squared plus ay squared, right? But if you are sitting on the inclined plane, not the inclined plane, on this block capital M, right? Then you also have an acceleration a to the right. That means between small m and capital M, there is no relative acceleration in this direction, but there is relative acceleration in this direction, because capital M has no acceleration in this direction, whereas small m has acceleration g in this direction. So refer to capital M. What is the acceleration of small m? G downwards. Refer to capital M, small m has relative acceleration g downwards. Why? Because in this direction there is no relative acceleration. That's a wedge constraint. Clear? So you know, this capital M is a compartment. This is the outer lining of it, and there, it has a cavity in which a block of mass small m rests, right? Now there are two cases. A force capital F applied to capital M in this direction, and a force capital F applied to capital M in this direction. In both these cases, I want to find the acceleration of capital M and small m. Okay? This case first. Let me look at this case first. See, capital M would want to move like this, right? Capital, and everything is smooth here. Capital M would want to move like this, right? Now look at small m. Look at small m. For small m to move in this direction, there must be a horizontal force acting on small m, right? Capital M at this interface must exert a horizontal force small f on small m in this direction. But when could this exist? If there was friction, but there is no friction. That means small m cannot move in this direction. What force will cause it to move in this direction? Friction, but there is no friction, right? How would small m move? Small m will therefore not move. So what is the acceleration of small m? 0, right? And what's the acceleration of capital M? F by capital M, right? Acceleration of, because only capital M is moving to the right, F by capital M is the acceleration of. Did you understand this? No. See, this outer block would move to the right because of this force, right? And if you want small m to also move in this direction, then somebody would have to apply an external force on small m, right? The only way an external force can be exerted on small m is, now this bigger block, capital M, cannot exert a smaller m a force in this direction. Yes or no? No? Nahin, na? That means the only way a force could be exerted on small m is frictional force to the left, but there is no friction between small m and capital M at this juncture, right? So small m will stay put, small m will not move. Acceleration of small m would be 0, right? Now, an acceleration of capital M would be so capital M will move independently in this case with an acceleration capital F by capital M, right? Now in this case, so it's just only a conceptual problem, nothing difficult about it. In this case, if the force is applied like this, now at this vertical interface, capital M can exert on small m. Capital M can exert on small m a force like this, and good enough for small m and capital M to move to the right with a common acceleration. Now it is not dependent on friction. In this case, the motion of small m to the left was dependent on friction, which was absent, so small m was left behind. In this case, it's not dependent on friction. It's a normal force between capital M and small m along this vertical wall that will cause small m to be pushed to the right with a common acceleration of same as that of capital M. So in this case, both small m and capital M will move with a common acceleration. Common acceleration A is going to be F divided by capital M plus small m. in this case. You got the same answer? Sure, na? 100% or only 80%? Please ask. This way, right? पीछे किसको? इसको? ये तो बेचारा वहीं रहेगा, उसको पीछे आने के लिए भी तो एक फोर्स चाहिए ना. फोर्स चाहिए ना to move, to accelerate in this direction. It will need a force ना भाई. फोर्स कहां से आएगा? If you pull this block to the right, this block will not unnecessarily push small m in this direction, है ना? That means for a small m to at all move, there must be friction here na, along the horizontal common interface. So small m will stay there. If you are sitting on capital M, small m will appear to move to in that direction. But है ना? But if you are a ground observer, small m will stay in position. हाँ? ठीक है?